Start.
Okay, hello everyone. Welcome to our first panel discussion session. So this panel is about trustworthy machine learning. I'm the host of this session. My name is Chen. I'm an assistant professor at National Taiwan University. And today we have four amazing panelists joining us. So let me first introduce each of them. Actually, two of them are also our lecturers, so you should have seen them before first, but I will still briefly introduce them again. So first we have Professor Cho-Jui Hsieh. Cho-Jui is an assistant professor at UCLA. His work focuses on improving the efficiency and robustness of machine learning systems, and he has contributed to several widely used machine learning packages. He's the recipient of NSF Career Award, Samsung AI Researcher of the Year, and Google Research Scholar Award. His work has been recognized by several best paper awards at top conferences like ICR, KDD, ICDM, and many more. He gave a lecture on neural architecture search 2 weeks ago. So, but he also has done a lot of work in adversarial machine learning. I heard from Pingyu that you two are working on an adversarial machine learning book, right? Yeah, so I'm really looking forward to the book. Yeah. And next, we have Chen, Dr. Chen. Pingyu is a research staff member at IBM Watson Research Center. He's also the chief scientist of RPI IBM AI Research Collaboration and PI of the MIT IBM Watson AI Lab project. Pingyu's current research focus is on adversarial machine learning and the robustness of neural networks. His long-term research vision is building trustworthy machine learning systems. Yeah, so you should have seen his lecture on adversarial machine learning. Yeah, so he's an expert in this field. Next, we have Soheil Feizi. Professor Soheil Feizi is an assistant professor at the University of Maryland, College Park. His research spans various theoretical and practical aspects of machine learning. He has been working on gaining deeper understanding of the robustness of deep learning models with respect to the learning architecture, model complexity, sample complexity, and different kinds of noises and attacks. He's the recipient of many awards, including the AWS Machine Learning Research Award, IBM Faculty Award, and Qualcomm Faculty Award. Soheil, do you want to say hello to our audience, our students? Yeah.
Hi, everyone.
Hi, welcome, Soheil. Yeah. And next we have Professor Sijia Liu. Sijia is an assistant professor at Michigan State University. He was a research staff member at the MIT IBM Watson AI Lab from 2018 to 2020, last year. And his research spans the areas of machine learning, optimization, computer vision, and signal processing and computational biology, with a focus on developing learning algorithms and theory for scalable and trustworthy AI. Yeah. So welcome, Sijia.
Nice to meet you. Hello, everyone.
So, I think I will first ask each of the panelists to briefly talk about their perspectives on the research of trustworthy machine learning, including what research problems they want to do or they want to encourage our students to work on towards trustworthy machine learning, and also some advice from their experience in this field. So I think we can go through with the same order. So maybe we can, Cho-Jui, do you want to go first?
Okay, let me share my screen.
Okay.
Ooh, okay. Okay, so I will just briefly introduce myself and briefly talk about what we're working on and what I think are interesting future topics. And by the way, I think there are many different areas in trustworthy machine learning. And for example, you have the gender bias problem, and you have the robustness problem. And I will mainly talk about robustness problem, which is my focus. Yeah. So so first, let me introduce a little bit about myself. So I'm a graduate from National Taiwan University, and my PhD is from UT Austin. I'm joined UCLA at 2018 as an assistant professor. And meanwhile, I'm also visiting scholar in several companies, including Google and Amazon. So so I'm not like directly working in a company like Pingyu, but kind of having some connection with people inside there. Yeah. Okay, so so I think most people are interested in a universal example mainly because it's very interesting problem. So I think long time ago people find if you add some like small perturbation to a image, you can make it the neural network easily misclassify. Like here, you can make a bag or a grand piano without adding much perturbation. And later on, many people working on different kind of models. Like this is, I think, my work with Pingyu on vision caption models. And also, there are more recent interesting example, like you can try to attack a reinforcement learning agent. Like this is in the first row, you make the reward negative. You can see this dog is moving very weirdly using his head to try to run in the environment. And in the second row, you can see this agent looks like the second column. This agent looks like working smoothly, but it's actually moving in the reverse direction. So even though it's very, so when you perturb the environment a little bit, you can make it moving to the reverse direction very quickly. So it becomes a very large negative reward. So and one important application for robustness should be in the reinforcement learning, because you are trying to make the real agents robust to environmental change. And also, I try to quote some Pingyu's work on universal t-shirt. So people are trying to create some t-shirt to evade from like an object detector. And also, this is something we're recently working on, because I'm like a Go player. So we try to study whether you can try to attack a very strong Go agent. So you can see if you try to perturb the board by a little bit, the win rate will drop from 99% to 10%. Okay, so my research mainly, I will try to understand the mathematics of universal robustness, and there are several directions. So mathematically, if you want to define the robustness, then it will be the distance from the original example to the boundary. And usually people care about the LP norm distance from the point to the boundary. So in the research of the universal attack, people try to find a universal example which can serve as the upper bound of this distance to the boundary. And another direction is you can try to find the lower bound of this boundary, and this lower bound can serve as a safety guarantee for the distance. So for example, if you have the orange radius, then you know anything within the orange radius will remain unchanged. So this will be some safety guarantee of your model. So the challenges, I think in terms of the attack, the challenges are in several folds. I think other people will also comment. So my opinion is there are lack of attack to the real problems, real models in the real world. And most of the attacks, even though there are a lot of papers, are in the TOEIC example setting, like CIFAR-10 or ImageNet. And also there are many attacks beyond evasion attack, which are less studied. Yeah, so my expertise is more in the verification. So I will talk a bit more about the challenges here. In verification, it's like you try to provide some safety guarantee for your model. Like in this figure, you try to compute the lower bound of the distance here. And this is the NP complete problem. So in 2017, people try to propose an exponential time algorithm called ReduPlex, which can only scale to 100 neurons, like a very, very, very small network. And this requires several hours to a day to solve one instance. So it's very impractical at that time. But after several years of the developments, you can see this is the VNN competition. So there's a competition on neural network verification, and they have like an annual competition. This is the data set we're using in this year. So you can see the data sets. They are not only computer vision, but also some control system and also some this is some system prediction problems. And many network has already reached like almost 10 million parameters in the model. So you can see we have a jump from 100 to 10 million. And most of and there are many tools participate this year, and you can see there are both GPU and CPU tools you can use. People can nicely solve most of these problems, and this is the ranking leaderboard. And fortunately, we got the first place in this year's competition. But the challenge in this field, even though we can increase from 100 to like 10 million, but we are still trying to find the real application. So currently, the most famous real applications is this ACAS2. So this is like a airborne collision avoidance system, which is going to be used in practice, and people try to verify this. However, this is very small network, and the input space is very small, so people can try to clearly define what do we mean by safe in this model. So when we try to do neural network verification, we need to define something called specification, which means mathematically, how do you say a network is safe or unsafe? So for a very small case, you can define it, but for other real applications, I think one of the challenges is how do you define realistic specifications that can be mathematical formulated and verified. And also there are challenges like many of these tools. I think all the tools, most of the tools can only nicely handle ReLU activation. Some tools can handle other activation, but may not get like a complete verification results. And also in this competition, people find there are so we have power law distribution everywhere. So in neural network verification, there's also power law. So some problem instances are very simple, but some are very hard. A very small amount of them are very hard, and that will take days or weeks. We cannot verify. So how do we tackle those hard cases? And finally, the challenge in defense, I think other people will also comment on this. So there are also some leaderboard for defense on CFAR 10 data, but there are also challenges in practice. Like one practical challenge we're facing when we collaborate with real applications is that many people care about distribution shift instead of like this kind of adversarial perturbation. For example, we have a self-driving car working in the sunny days. We want it to also work in the raining days or the snowy days. So how do you make your network robust to natural perturbations or out of distribution data? And how do you use this robustness as regression to improve the performance of network? So all of those are very interesting questions. Okay, so that's the that's all my slides. Thank you.
Okay, thank you, Joy. So everyone, please feel free to type your questions here at the chat. So, and then we'll choose the appropriate questions to ask our panelists. So while we are waiting for people to type questions, we can move on to the next panelist, Pingyu, do you want to also share some of your insights?
Yes, sure. Let me share my screen. Oops. Let me know if you can see the full screen or not, because I have two screens and sometimes the sharing. You see the full screen or the speaker mode?
It's in speaker mode now.
Okay. How about now?
Yeah, it's good now.
Okay. Yeah. So I think it's very nice that I followed after Cho's talk, right? So yeah, I want to kind of share my thoughts on the trustworthy machine learning. I really know from the deepest of my heart, believe this is the most important milestone to achieve, right? After we see the first wave of success in deep learning, right? Like AlphaGo, AlphaFold, and all those exciting breakthroughs like large language models or so. It seems like deep learning is really revolutionized our life and our technology, but the next important thing to make them realistic and useful is to ensure these tools to be trustworthy. And to make that happen, right, the important tool that I'm going to talk today is adversarial machine learning, and I add for good, right, in this title. So it kind of has a twofold purposes, right? For good, usually one purpose is that how can we do something, right, to benefit the mainstream machine learning, right, instead of staying in the field of adversarial robustness and so on. The other meaning of for good is that how can we make this new and young research area more sustainable and even thrive as much as it is right now. So let me start by mentioning the elephant in the room, right? So as the AI researchers, we all know there is a gap between how we develop AI versus how we deploy AI, right? So when we develop AI, we kind of assume everything is ideal, right? Data and training and testing data are sampled from the same distribution. When we deploy data, there is no distribution shift, as Cho mentioned, and there is no adversary in the room that try to disrupt our service. But that's what actually not the real world is, right? Real world is usually contains a lot of unseen data and unexpected scenario that will degrade our machine learning's performance. Not to mention there could be some enemy in the room that try to leverage or break your system to gain their own leverage. So that's why we care a lot about robustness, right? Not just adversarial robustness, but like natural robustness in general. So I would like to start by kind of motivate these issues, right, from the aspects of trustworthy AI themes that the IBM has developed a few years ago, right? So I think IBM noticed this issue is very important for AI technology to be trusted and to thrive, right? So and under that, the trustworthy AI theme, we defined 4 different pillars that we believe to be the most important to address, right? Including robustness, right? Making sure your model, right, is robust, making robust decisions against the natural or adversarial environments, and also fairness, right? Making sure your model's prediction it does not create any discrimination against any population or any group. You also want your models to be explainable, right? You are able to explain its decision and how it makes that decision. Finally, linear edge. So it's about adding transparency to our model and our service so that it will facilitate AI governance, AI regulation. So I also want to give a different perspective from how the government, right, or other agencies are defining trustworthy AI, right? So if you look at how European commissions are defining trustworthy AI, they require trustworthy AI to be lawful, right? To obey all the laws and regulations, and to also to be ethical, right? It should not be doing harm or unethical actions. It also needs to be robust and prevent unintentionally harm to our safety and our society. If you look at this GDPR rules, which has been implemented in many countries, right? There are specific rules to ensure the service, right, AI is providing should be integrable, and also confidentiality has to be met, and also it needs to be accountable. So there are many reasons, right, not just from a research perspective, but from a practical perspective, why ensuring trustworthiness of AI models are very essential in this AI technology. Then I kind of want to make a connection, right? From my view of adversarial machine learning is really about introducing a methodology to learn with an adversary in your environment. And that introducing that adversary really helps you to understand and investigate and also improve your model's trustworthiness. Right, so from adversarial robustness perspective, right, introducing adversary can really help you to understand your model's performance in a worst case scenario. And you can often introducing adversary during this model training, right, can help your model to generate these artificial mistakes and learn from those mistakes to improve the robustness. So we have seen a lot of successful examples of using this adversarial machine learning idea, including generative adversarial network that you introduce this discriminator during training to make sure you can generate high and fidelity synthetic images. And we also seen like a very interesting application from OpenAI. They introduced this hide and seek, basically a zero-sum agent training environment, and eventually all these hiders and seekers learn very non-trivial and creative rules to play hide and seek. On the other hand, we also one reason we want to study adversarial machine learning is to be proactive, right? So as the AI technology become more and more advanced, right, there is no prevention from these adversaries using AI to gain their leverage. So it's also very important as a model researcher and model developer, we need to be proactive and actively testing the robustness of our machine learning models by ourselves before the real damage has been done by these outside malicious users. So with that in mind, I would like to share my thoughts on this, how can we achieve holistic adversarial robustness, and we can go to more details in the later discussion. So ideally, to achieve this holistic adversarial robustness, we will hope our methods will be model agnostic, right? It can work on different data modalities and also different models, but it also needs to leverage these domain-specific knowledges to maximize the robustness properties. And most importantly, it also needs to be practical, right? So we certainly don't want to harm our model's performance by increasing the robustness. And this practice should really be carried out through the life cycle of the AI model, spanning from training time to testing time to monitoring when you deploy your model. And under this theme, right, we can really talk about the different terminologies, right, in terms of attack, defense, verification, and applications to AI. So for attack, right, we are really care about is how are we able to find any bugs, right, hidden in our model, and that basically relates to this white hat hacking or ethical hacking, right, to actively search for potential errors in your system before you actually deploy that system. And once these errors has been identified, we will move to a defense stage, right? How can you detect any hidden errors in your system? And once they are being detected, how can you mitigate those errors? And ideally, you would want to mitigate those errors in the plug and play manner. So you can give a model and then try to do some fix on that model and return a clean and robust and secure model back to the user. And finally, is verification, what Cho has briefly mentioned. How can you build this quantifiable robustness metrics to benchmark and ensure a certain level of reliability for your AI system? And finally, I think it's also something that is kind of has been underlooked in the past is once we know these AI models are vulnerable, right, or once we know how can we make those models more robust, what are the interesting applications that we can introduce to the machine learning society, right, including using these adversarial examples as data augmentation or reprogramming your model to solve a new problem in a more data efficient way. So I've seen more and more applications like that, and I think this is certainly the way to go to make the whole adversarial machine learning field grow. Finally, I would like to share some trends, right, I observed in adversarial machine learning. Right? So if you look at the number of papers we publish at arXiv related to adversarial example, right, we do see this exponential growth. Right, but when I look at this curve, I start to wonder, right, will we keep growing, right, the next year, or we will see some saturation or even some drop, right? And that's certainly not something not ideal. Right? We certainly, as a community, we certainly want this curve to grow at a steady speed. So that basically means we need to be more creative and more open-minded, right? And I would like to share some of the lessons I learned, including myself, are constantly making these like incremental steps, right? Although they are easy, right? So for example, in the attack field, we also see some papers like adversarial attack on certain tasks, and then black box attack, and then hard label attack, efficient attack based on certain perturbation norms and so on. So and for defenses, we see very similar trend. We got defending against a specific adversarial attack using some method, detecting those threats, certify robustness for certain tasks and norms, and adversarial training using some techniques. I think these are all great topics, right? But if we keep doing this, and instead focusing on something new, right? I don't think this area will really thrive, and then we might not be making enough research progress as we expected. On the other hand, I also think there's a lot of insights, right, that can learn from these recent trends, right, including a lot of reflection papers to study why all the empirical defenses should not be trustworthy, and they are all vulnerable to new types of attacks. And also a lot of discussion on how can we make the threat model more practical. How can we leverage or evaluate a new neural network architecture like a vision transformers through these adversarial machine learning techniques? Or can we have a more like a broader view in terms of understanding the trade-off between adversarial robustness and any other factor that are important in trustworthy machine learning, like privacy, fairness, and interpretability. So I think all these things are like great topics, but again, to make this the deltas in the future for this community, I really hope that we can be think outside of the box and be more creative, and really do something that will bring totally new contributions to this field. And lastly, to provide some motivation, that this is of course up to debate, right? I try to motivate how difficult it is nowadays to publish a defense in these top AI conferences, right? So if you want to claim you have a new defense against all these adversarial attacks, right, you will start from here, and then the reviewer, as a reviewer, they will see if you first test it on any white box attacks, right? And if yes, then you go to the next question, like, oh, did you test on an auto attack? That's the ensemble of recent white box attack. And if yes, then you will encounter the question: is do you think your model has any gradient obfuscation issue? If no, then the reviewer will ask, oh, is your model provably robust? If you pass that, then how is your model compared to this randomized smoothing technique, which is the state of the art certified robustness? And finally, the PQ reviewer will say, okay, I notice you have a drop in your clean accuracy. Do you see a drop? And if your answer is no, the reviewer will say, oh, there is no free lunch. It's almost impossible to have a more robust model without sacrificing other factors. So nonetheless, the decision will be, no, don't publish your defense. There must be something wrong. No, I want to put this chart and up to debate. Like, I think nowadays we are putting a very high bar on accepting the defenses, which may not be ideal to our field. On the other hand, we certainly understand a defense, right? If it's truly useful, they should really, be ideal and satisfy all the requirements, being robust, being certifiable, and also does not drop test accuracy by any margin. But do we have that such defense exist, right, in the real world? That's also something I hope to discuss during this panel. Thank you.
Yeah, thank you, Pingyu. Yeah, I totally agree on this your last this slide. Yeah, I feel like it's much harder to publish a defense paper now than in, say, if you are doing attack, right? So when you do defense, people will be skeptical about your approach, especially if you are doing empirical defense. People say, oh, you don't do black box attack, you didn't do black box attack, you didn't evaluate on ImageNet and so on. So for example, I think Nicholas Carlini has published a paper on how to evaluate the robustness of your model, and it's like a 24 pages paper with a lot of this. You should do this, you should do this. And if you don't do this, he will maybe will publish an archive paper breaking your model in a few weeks or something. So it's very hard to publish now. Yeah.
Exactly. Totally.
Yeah. So I see there's a question from our students. Sen Woon is asking, he says, I wonder whether perfect trustworthiness can ever be achieved. I'm afraid even not. There are 2 points. One is even a simple mechanistic system, for example, a manufacturing line cannot achieve 100% reliability. And number two, human perceptual systems are not trustworthy. So if 100% trustworthiness is not achievable, what would be the realistic goal that we can work on? Yeah, so yeah, I think that's a good question. I think the main question is what kind of trustworthiness should we aim for, or should we be looking for? Yeah,
do you want me to take that question, or?
If you want to, you can answer. Please go ahead, and other people can jump in later. Yeah.
Yeah, so in my mind, like a trustworthy or not is not really a binary question, right? I think we can certainly, it's more like a spectrum of when you evaluate trustworthiness, right? Like one region is like one extreme is like is no trust at all, and the other region is like totally full and ideal trustworthiness. And I think ideally we should be something in between those two extremes. And I certainly think we are able to formally mathematically describe what do we mean by trustworthiness, right? So for example, at least for adversarial robustness, there are like some threat models, right? Although some people may think they are too realistic, not too like simple, right? But at least we have some models like LP norms, perturbations, and so on. So we can start from there and gradually build different levels of robustness, right? So we can ask questions like, okay, if your model is robust to certain LP norm defense, right? I will give you like 20 or like give you like a B, right? Or if you further pass a certain level of adversarial attacks, I will give you a B+ and so on. So I would say there are certainly different levels of robustness we can quantify, and we can benchmark our progress little by little until we reach the full robustness goal we want to satisfy.
Okay. Yeah. Any other our panelists want to answer or give some feedback on this question?
I think from my point of view, 100% of trustworthiness is not the goal. So if we think about adversarial robustness, we have a Silverton data set or IMINET data set. If we consider standard accuracy, we can have, for example, takes IMINET as an example, we can have around 80% accuracy for the IMINET 1000 classes classification problem. But what we are not allowed is we have 80% standard accuracy, but we have 0% robust accuracy, which means it's very easy to attack. So this is always a game. We want to find the best sweet point between the robustness and the accuracy. We want to improve the accuracy, which means the generalization of the model, but without a loss of the huge loss, without a huge loss of the robustness in terms of the trustworthiness. So this is so therefore 100% of trustworthiness may be not realistic, but we need to try to improve that. And because 0% of trustworthiness is not ideal, right?
So yeah, I think I have a follow-up question. So you also mentioned that a lot of this threat model is on small LP norms. And we know that small LP norm are not maybe a good metric in many applications. So people propose other different threat models like physical attack, like doing adversarial patch style attack. But sometimes it's more difficult to formulate this kind of threat models like in small LP norms. So it's harder to compare different threat models and different settings, and so it's hard to compare the robustness or trustworthiness of different systems or models. And yeah, so and also sometimes, so there's just so many threat models. And even though if your say your model is robust against small LP norm threat models or attacks, people can say, okay, it's still more vulnerable to other attacks, other kind of threat models. So it's in this case, it's worth it. The worthiness is more tricky to claim. Even so, you say you can claim trustworthiness in certain settings or threat models. There will be so many other ways that those models can be attacked.
Maybe I can jump in here, just to follow up on this point. It's a great point, that, I would say, a wide majority of the research in robustness focuses on like LP threat models. And also, even if we focus on non-LP threat models, the assumption here is that the defender knows the threat model the attacker is going to use. Right? Even if I'm assuming that my defense is robust against, let's say, Wasserstein threat model or different types of semantic threat models that we can consider, the underlying unrealistic, I have to say, assumption is that, okay, so there should be a matching between the two threat models that the defense and the attack are being used. But by definition, adversary is not going to be a nice person, right? So adversary can just change the threat model it uses in order to break the defense that may be extremely robust against certain threat models, even provably robust against that. And that's basically the topic that's called generalization of robustness, which in my opinion is severely understudied in adversarial robustness. So I can maybe advertise a little bit of our recent work in this topic. So one of the ideas that we have proposed here is to, so consider a set of imperceptible adversarial examples. The key challenge here is we don't have a good mathematical characterization of human perception, right? That if we had that, we wouldn't have many of these problems. What we do is we try to fill this up using narrow threat models. We try to say, okay, LP is a good threat model, Wasserstein, patch, different types of semantics. And we try to say, okay, at the end of the day, if I have a model that is robust against union of these narrow and small threat models, I'm going to be good. But the problem is that there are many, many adversarial examples that may fall outside of the union of narrow threat models. And that's basically the key challenge here. So one idea that we have proposed is to, instead of this bottom-up approach, to fill basically this set of imperceptible adversarial examples with narrow threat models, we do a top-down approximation. We directly approximate the set of imperceptible adversarial examples, let's say using a neural network, using deep learning itself. And of course, there are several new challenges using this approach, because now the threat model itself may be vulnerable against small perturbations. And also how we can even evaluate the approximation, the quality of a neural network in terms of approximating human perception. So surprisingly, we have observed through human studies that neural networks are pretty good in approximating human perception. So if you show two images to a neural network, certain measures of neural networks, and basically compute the perceptual distance between them, it somehow correlates well with how humans would perceive them. And that kind of encourages us to think that this may be a new direction in terms of understanding generalization of robustness. So that's an important topic. So let me just pause here and see if there are other thoughts on this topic. Otherwise, I want to add a little bit about some other topics that were previously mentioned.
Yeah, I think maybe Soheil, you can go ahead and share your other insights. Yeah.
Okay. Sorry, I don't have slides.
Just talk.
Slides you, so I'll just talk. So I think there were like really great points mentioned by the previous panelists in terms of, trustworthy ML. So first of all, we don't need to only focus on one aspect. Right? Robustness is important, but it's not the only aspect. So we have fairness, we have explainability, you name it, privacy, ethics, other aspects. And I think one of the interesting directions for future studies is to understand interactions between different aspects. For example, you have some measure of explainability. Is it robust? Or you have a measure of robustness. Is it explainable? Same for other measures. You have fairness, right? So, is your fairness measure robust? Or can you think about adversarial fairness in terms of, for example, some, subpopulations and how sensitive they're towards adversarial examples. So that's, I think, one direction that, hopefully in the future we'll have a better understanding of. And of course, the underlying challenge of all of these problems is that, we start with some very well-defined tasks, right? We assume we have a probability distribution. We assume we have an objective function. We can, decode and encode, some, cost functions or rewards functions or, many of these optimization objectives that we write. But in practice, that may not will be the case, right? So there's definitely a gap between what we formulate and what we observe in practice. So we need to also have a little bit of a better understanding of this gap and how we can close it in the future. And other point that I just want to briefly mention that it's in terms of robustness of adaptive learning, right? So we have studied robustness of deep classifiers for quite a bit, right? So you have a lot of methods that claim robustness on CFAR or ImageNet or you name it, different data sets for image classification. But what about reinforcement learning that was mentioned earlier? Right, so that's a significantly more challenging problem, and believe it. So we started thinking, okay, maybe we can take some of these provable robustness techniques and directly apply to reinforcement learning and get certified robustness in reinforcement learning. And we immediately realized that problem in reinforcement learning, in adaptive learning, is orders of magnitude more challenging because of the sequential nature of the adversary that you can have. The adversary can be adaptive itself. Right? So you have a game, adversary can observe the way that you are defending, and it can adapt itself to the defense applied in previous times. Therefore, we need to develop very specific and more mature techniques for such adaptive learning. We extended some of those lemmas that we used in provable robustness recently, like Niemann-Pearson lemma, that is one of the foundations of many provable robustness. But I think in the future, there are many open questions in this domain. So I just want to briefly mention some of these areas, and I'll just pause here and hand it back to you, and I'll be happy to take more questions.
Okay, I see there's more questions, but I think maybe Sijia, you can share your thoughts first. Maybe you will already answer some of the questions here. Yeah.
Okay.
So go ahead. Yeah.
Maybe I can present, and some questions actually covered in my slides. So we can start from there. Okay, you can see my screen, right?
Yes.
Okay. Okay, great. Yeah, that's a great pleasure to be here to talk about the challenges and the opportunities for the trustworthy machine learning. And here, before talking about some focused research challenges, I want to give a very brief introduction about myself. So I did my PhD degree at the Soheil University in 2011 to 2016, and then I was a postdoc at the University of Michigan, Ann Arbor, and spent almost 2 years. And also, Ping and I, we were in the same lab at Michigan. And then in 2018, I joined the MIT IBM Watson AI Lab as a founding member. And recently, I joined the CS department of the Michigan State University as an assistant professor. So So since 2018, I started to work on trustworthy machine learning. As you can see, this is quite a young field. I think the start from the 2016 or late 2016. But as PE showed, there's a curve, the huge explosive number of the papers published in this field. And why? Because of there are many unresolved questions remaining here. So in my part, I want to describe 3 focused challenges that I found quite interesting in my research. And first of all, I want to talk about from the attack perspective. So this is called reverse engineering of deception. So usually we consider attack generation, and attack detection, and some adversarial training for defense. But both detection and defense usually build upon the rejection decision, which means we want to know whether this attack, whether this example is attack or not, or how to reject this adversarial example. But in another perspective, we can also consider how to reverse engineer adversarial perturbation. Let's take adversarial example as one perspective, because we can learn, we can gain information about the adversarial itself, why they attack this model and how they attack this model. So that's another dimension of the adversarial machine learning problem. This is called a reverse engineering of deception. I will introduce this later. And the second challenge I will mention is from the defense perspective. So I'm trying to challenging the best or the validity of the current algorithm foundations of adversarial training. So as we discussed earlier, we really want some defense which is attack agnostic, which means threat model agnostic. And how can we build up such a defense? And anything we should consider beyond the min-max adversarial training automation framework. So this is the second challenge we have, and this is a huge challenge, and we really want to solve it. And I will also cover this challenge. And the third challenge I want to discuss is from the system perspective. So we also mentioned a lot of things as we just discussed. In addition to robust, we have many other performance metrics to evaluate a system. So therefore, I call robust to X challenging. We need to give a very complete view of the robustness to understand how the model performs. So these are 3 main challenges that I will cover. So the first challenge, as I mentioned, we should look at from the attack rhythm, from generation, rejection to reverse engineering. So existing work, we usually focus on how to evaluate the worst case robustness of machine learning models. So to address these issues, we usually generate either white box or black box adversarial attacks. And people already found that attack exists and it can be generated in many ways, as well as in different scenarios. For example, in the digital world or in the physical world. Like Chen mentioned, one example is called adversarial T-shirt, published at 2020. People found that you can wear a T-shirt, even the T-shirt suffers from the rigid transformation, but still it can fool the object detectors. So this is one examples of the physical adversarial attack. So generating attack is not so difficult, but what's a real difficulty? So so if we recall the machine learning pipeline, we already have from data to the model and then to the inference to the prediction phase, right? So we could suffer from the attack in both training data phase or the prediction phase. So the training data phase, people usually call the data poisoning or Trojan attack, like test time adversary includes adversarial examples, so on and so forth. So think about this is a machine learning pipeline which suffers from adversaries at both training time and test time. So one quite interesting question is different from defense and attack generation is which is called reverse engineering of the deception, the RED. So this is trying to reverse engineer attack 2 chains. I will define 2 chains later, but we want to reverse engineer attacks rather than just rejecting in terms of either detection or robust training against those adversarial attacks. So let's take examples. For example, if we consider the train time attack, so the reverse engineering of deceptions, basically you can consider how to recover the techniques used by the adversary to pollute the training data. So one example is called a Trojan attack. You can estimate the Trojan trigger used by the adversary. So this is something different from just the detection of the adversarial instances, right? Because here you want to give more information about the adversary. Why is the adversary and what tools they use to attack this model? So similarly, at the test time phase, we can also consider reverse engineering of deception for test time attacks. Let's take adversarial example as a typical instance. So we want to recover the pixel level perturbations, right? Or we want to recover the attribution level attack silence image regions. So where in this image attack trying to perturb and then for the model, we want to give some information about attack itself. So this problem, this challenge is called reverse engineering of deception. Actually, this is a project funded by DARPA. And for example, Soheil is also involved in this DARPA project. So this is for the challenging from the attack perspective, how to reverse engineer of deception. So this is different from attack detection and robust training. So this is the first challenge I want to share. And the second challenging I'm trying to consider is from defense vision. So how can we generate attack agnostic robust training protocol? So let's recall, so what's a best recognized robust training framework that we use so far. So we use a min-max alternation-based adversarial training, which is proposed by Madri at 2018. So this is a very good robust training framework. You just consider min-max alternation, which is trying to train the model, which is minimize the model parameters subject to some worst case training loss against some input perturbation, delta. The delta here is trying to maximize the training loss. So this is great. So it has been achieved great performance against the LP robustness, right? But however, there's some assumptions. The assumption is we need to assume the attack and the defender, they share the same objective, right? For example, the attacker and defender must consider some perturbations or some robust model parameters just within the limited region of the L-train. L-train here is just a training loss. So these are assumptions I call attack-specific assumptions. You need to consider this is a theoretically aligned attack objective and a defender objective. However, in practice, their objective could never be aligned. So this is challenging. So therefore, we need to think about the fundamental approach to address these issues. So this is what I call, we need to consider what's the best approach for attack agnostic training. So one possible way we can do that is we can extend or generalize the min-max alternation to the bilevel alternation. So the bilevel is a kind of like generalization of the min-max alternation. You just consider the attack generation as the conjoint problem of the model training. So in that case, you can, using the model training, you can consider the training loss, but for the attack generation, you can consider different attack loss, even in simple attack loss. So this will give you different formulation. However, it will also give you different alternation routine to solve this problem. So this is called bilevel alternation. So I think the bilevel alternation could be very useful to generalize the robust training protocol to devise the attack agnostic defense. So this is something I want to share, and our lab also has some ongoing work along this direction. It achieved great performance. And the third challenging, as we mentioned earlier as well, so we want to consider robust 2x. So we have, for the deep learning model, we have many aspects to evaluate the system, right? So for example, we have interpretability metric, as we mentioned earlier, and we will have uncertainty, and we will have test accuracy, sparsity, which means the model compression, and even non-adversarial robustness, like out of distribution robustness and fairness. So we have many metrics. So therefore, we need to ask the following questions. Okay, what's the trade-off, or is there a trade-off between robustness and other metrics? So this is called robust 2x. So indeed, there are some recent work and existing books to trying to consider this problem. For example, people have quite a good understanding about robustness and accuracy trade-off. And even some recent work said there's no trade-off. It could be there's no trade-off. But this is some well-studied topic about robustness and accuracy. And besides, people also talk about robustness versus sparsity. So the model inference efficiency. So can we preserve robustness as well as compress the model simultaneously? So this is also some questions we, including my lab, we are trying to work on. But this question is still not fully answered. So there are different opinions. So one is robustness can be preserved without sacrificing the model accuracy and sparsity, but some paper, some research work said the negative results. So this is still quite an open question to be answered. And also, there are robustness versus out of distribution robustness. So adversarial robustness versus distribution shifts. So there are two different robustness metrics. Whether there's a trade-off between those two metrics or not. So this is also quite an important question to be studied. And furthermore, there's a robustness and the fairness trade-off. There are several recent papers trying to talk about that. But however, there's a changing from fairness itself. So fairness can be measured from different aspects. So therefore, if we really want to understand how robust the model is versus how fair the model is, we really need very careful studies here. Consider different fairness metrics. And also we have the robust and versus model interpretability. So ideally, we can think about a better interpreted model should have better robustness because more interpretable model is more aligned with the human, and the human usually is good at robustness. So however, the case may be not always true for the deep learning model. Therefore, there are some works along this direction as well. So as you can see, the robustness to X changing is quite broad, and therefore it requires quite careful studies here. And lastly, I want to conclude my statement about the challenges and the opportunities using the Cher's words. So now it's not the end. It's not even the beginning of the end for the adversarial machine learning, but it is perhaps the end of the beginning. So I think that's all from my part. If you have any questions, feel free to ask.
All right, thank you, Sijia. So yeah, we have more problems from the students. So one is from Tong Fang. He's asking, so Tong is asking, I'm wondering if the defenses attacks happen in real world scenarios are the same as those that appear in the research papers or not. Is there a gap between what we develop in research and what happens in the real world regarding the methods of defense and attacks? Yeah. To anyone wants to answer this question, give your opinions.
Yeah, I think the gap always exists, and so far, usually we consider LP robustness, right? But clearly, this is not the best robustness we desired in practice. So there's a gap there. But achieving robustness is not free. For example, even for the LP robustness, it's easily to formulate, but training a robust model is not easy. So, so therefore, if we consider more complex threat models, and we still want to achieve a universal robustness, it's very challenging from my perspective.
Yeah, so yeah, I have a similar question, related question. So adversarial machine learning can be an interesting research problem of its own from the machine learning point of view, but people tend to connect it to security, like security issues. Probably this makes the research problem more important to and then easier to sell. And do you think that adversarial attacks really like become a security threat in real applications? So, for example, do you think we should worry about adversarial attacks for self-driving cars, or should we focus on other things first, like driving under undesirable conditions? Yeah.
Probably I'll take this. So I think both problems are important and worth studying. In terms of adversarial attacks on self-driving cars that you mentioned, there are physical attacks, right? So you can print some adversarial patches and put on stop signs, and that can mislead the vision systems. For example, used for the detection of some of these signs. So therefore, it can potentially be a security risk, especially if you have a lot of self-driving cars on the street. So it's an important problem practically. And also, I think PingYu has done also a lot of work on poisoning attacks, that we scrap a lot of images from the net, and some of the images can be poisonous, and it can lead to some undesirable property in the test time for some of the models that we train. But of course, understanding other types of robustness to distributional shifts, to domain adaptations, it's critical in probably more application domains, because you probably will observe more such cases when you have some test samples or some test environments that may not follow exactly the assumptions that we use during the training of the models. And I think that problem is also practically very interesting. But I wouldn't say one way or the other. I think both problems, they touch different aspects of robustness, and in my opinion, both of them are worth studying.
Yeah, I want to add to Soheil said, I'm very glad we don't have any security researcher in the room. Otherwise, the conversation will be very interesting. So I always notice the difference between how machine learning researchers view this adversarial machine learning versus how security researchers think about this question, right? So for me, at least, right, as a machine learning researcher, I don't really expect the adversarial machine learning will solve the security issue. Right? That means you can develop a secure and no one can break defense, right? And it also needs to be realistic and like threat model free and so on. But for me, I'm more interested in, as what Soheil mentioned earlier, right? How can we bridge the gap between generalization under the worst case, right? When you have a distribution shift, when you have like some small perturbations that's supposed to not change the model's prediction, right? That kind of thing is basically indicates our current way of training machine learning has some limitation. And how can we address that limitation and bridge the gap? I think is what will bring the success of machine learning. And whether that success will lead to solving the security problem or not, I think that would be a separate discussion. But the main focus should be how to understand how can we make machine learning model generalize better and adapt to a new environment quickly without this performance degradation.
Yeah, so I totally agree. I think there are like a kind of two driving forces in this community. The security people are trying to, like, I think like Pingyu, Sijia, and we have a KDD workshop and we invited some security people there. They are talking about all the current research are not realistic because you don't really break the system. But I really think we need both people, like security people, they try to really applying it in practice to see what's the challenge. And then as machine learning people, we are more interested in like mathematical problems, like what I mentioned in the slide. We have a point, we try to compute some distance from the point to the decision boundary. And then once we can extract most important challenge in the real world attack, we can try to resolve this problem either in terms of evaluation or defense. Yeah. And also on the self-driving car application, I think because I was talking with several self-driving car companies, I think the currently the challenge there is how do you define, like what I mentioned, how do you define the thing you want to be robust to? Like I use the term specification, it's from the verification community. Like even very simple thing is very hard to define. Like there's a guy talking about if you see the object in front of you, you need to turn left or turn right. But even this very simple thing, how do you define there's a object in front of you based on the input image? Because this, you can use some object detector like a neural network, but itself will be vulnerable. So how do you mathematical define what you want to verify? I think that's the main challenge. Like even in the patch attack, you are saying you have some patch on the stop sign, but in general, it's just seeing the whole image. And how do you specify there's some region perturbed on the stop sign or something? So it's kind of hard in practice. But I think that's also, I hope the security people and machine learning people we are both working on our thing, and finally we can converge to some feasible solutions. Yeah.
Yeah, I totally agree. Yeah, so I think security people are more practical. Sometimes they say, for example, when you say, so Soheil mentioned that there's you can put adversarial patch or stickers on traffic signs, but people will say this may be an illegal way, and so if it's illegal, why not just use like some other easier way, say replace the sign with other other things or remove the sign or break the sign. And also in terms of defense, there's other maybe easier ways you can put in your system, say for example, using the GPS signals or other things to help to defend against these kind of attacks. But I think because we are machine learning summer school, so maybe machine learning, we are machine learning people, so we are more focusing on the machine learning part of the whole system pipeline. So yeah.
Yeah, maybe I can add one more thing here. I think the goal of the adversarial machine learning take example is not just for security, right?
Yeah.
So take example, for example, several recent papers, including our own work, found that promoting robustness helps model interpretability, right? And also some recent, I think, paper from MIT, they found that promoting robustness helps transfer learning. So those are actually quite good things to build not just a secure model, but also better model in terms of even accuracy and other metrics. So these are all benefits from the robustness and adversarial machine learning. So not just for security.
Yeah, I also want to add to Sijia's point, right? I think other than the image domain, right, in the natural language processing domain, people are actually using adversarial training as a very efficient way to improve model performance on their benchmarks, right? So they have a very similar benchmark, like a glue benchmark that's equivalent to the ImageNet competition. And I think recently there are a lot of teams introducing adversarial training to generate adversarial examples and improve the standard accuracy on those tasks. So this is really beyond security, and it's even helping the mainstream, the standard tasks to perform better.
Okay, yeah, thank you. So we have another question from students. Jun Hong is asking, what's your opinion on adversarial robustness versus model speed? If a model needs an extra step to check or for adversarial attack, the real-time performance will be slower. So yeah, so should the model check whether it's like a false alarm or adversarial attack or react, or they should react immediately? Basically, he's asking about the trade-off between like robustness versus performance or speed. Yeah. Anyone want to give your opinion?
Jump in here. So it kind of depends on the defense deployed, right, in the model. You know, there are some defenses, for example, based on adversarial training, that the extra cost, the training costs, you know, or computational complexity is on the training side. So at the test time, we just have a robust model. So there is no difference in terms of the inference time that you have. But there are some other defenses based on smoothing. For example, you are adding noise, different realization of noise in the test time. And you need to, for example, add it like at least 10,000 times. And then you have like 10,000 feet forwards in order to have a robust model. And therefore, in applications that you need speed, you know, those defenses won't be a good fit. But if you just have a robust model, I don't think there will be a trade-off between speed and robustness.
Okay. So if no one wants to add thoughts, we can see on another questions. So Tong is asking how to break the circle of designing a defense B for an attack A, then designing another attack C for defense B. It seems there's a defense that we can design attack for it and vice versa. Basically, it's about the arm races of both the attack and defense. Yeah. Any good advice for students in this research area?
Yeah. So for maybe I can jump here to answer the question. But other, please feel free to add. I'm only saying my own opinion. So for I think this is an interesting problem in this field, and that's also the motivation why we want to work on verification of neural network. Because like in the picture, if we can, for any point, if we can compute the exact distance or exact robustness score, then we can guarantee this is the robustness to like epsilon equal to 0.03 perturbation, and no stronger attack can break this. So that's the reason why people are interested in study like complete verification, which means you try to compute exactly whether there is any adversarial example within this region. But it's also a very hard problem. So we can only scale to like currently you can do like millions of neurons, but still challenging for real world models. Yeah. And another comment I have is recently we're thinking about this problem, and this is also what we lack in the attack. So currently the attack is like you run, for example, PGD for 100 iterations, 1000 iterations, and it will stop decreasing the accuracy. And then you can say, maybe this is my robustness. But all the current attack, you cannot guarantee it's keep improving. So like if you run PGD for a very long time, it will still convert to a local minimum, and it cannot give you the exact measurement of how robustness is the model. So I think one thing we're lacking in terms of attack is what kind of attack can keep improving itself and eventually convert to the exact robust value. If we have such attack, then we can just run it for a very long time. We don't need to worry about this problem. But yeah, that's also what but we don't have any good idea how to do that. So yeah.
Yeah, thank you, Cho-Jui. So also speaking of verified robustness or verified accuracy, we know that verified robustness sometimes like very computationally expensive, and the verified the certified accuracy may not be very high in like real world problems. Do you think it's possible to keep improving to like usable or like very high, reasonable, high, robust certified accuracy like in the future?
Oh yeah, so there are two kinds of verification. In complete verification, you try to compute like a lower bound of the robust accuracy. So in that case, it's true that what you compute may not be very useful in practice because it gives you very small, like a robust accuracy. But there's also complete verification, which means it's like the bound will keep improving until reaching the exact value. So we're using like a branch and bound technique. So basically, if you have a redo neuron, then you can try to branch into the negative region or positive region. And if you do this branch and bound for every neuron, then it's guaranteed to break the problem into many linear subproblems, and you can solve it. So in complete verification, it can get the exact robustness for the model, but also you can imagine you do branch and bound, so it's very slow. So that's the challenge there. And currently, I don't have a good answer whether this will eventually work or not. Yeah.
I see. Okay. So there's another question from Sen Woon. So I think he's asking about the difference between LP, small LP attack and physical attack. But I think we kind of already addressed that. They are just different threat models. So another question from Obona. Obona is asking, reverse engineering and detection in the physical system, how can we distinguish between real-time attacks and system failure? Yeah, I think this is an interesting question. Yeah, because there's sometimes just system just doesn't work. Yeah.
Yeah. Maybe I can take this question. First, to give some my opinions. First of all, this is a very good question. So if we talk about the detection versus reverse engineering, usually we assume that we have a very good detector can detect whether or not this example is adversarial or not. But however, there are always the case there exists missing alarm and false alarm, right? So I don't think this can be avoided, because even for the detection, the standard detection program, you always have a missing alarm and false alarm. So but therefore, the goal for the reverse engineering should be, it should be to be insensitive to benign example, which means even though the benign example is used as the input of the RED, but the output should also be a benign example. So then you can still use this to do the prediction. So it doesn't matter. And in the meantime, the RED block should be very sensitive to the adversary example, which means for the adversary examples, even it's just partially perturbed, but once this is used as the input of the reverse engineer, so then you should still be able to recover the benign example, which means remove the adversary noise. So therefore, given the imperfect detection performance, we should try to build a quite robust or adaptive RED block, so that it's very sensitive, very useful to the adversarial example, but it's insensitive to the benign example. Yeah, so for doing that, you can close the gap between the detection and reverse engineering.
Yeah, and also I think I also have similar questions related to this. So sometimes we don't know it's an adversarial attack, or it's just like out of distribution data, or like very rare data, or not outliers. Do you have any comments on that? So if we know this data is an attack, we can do more things to prevent similar things to happen. But sometimes it's just like outlier data, yeah, or natural data. Yeah.
Yeah, I think this is a great point, and that's what my thinking is. It's very difficult for us to achieve the ideal adversarial robustness we want for image domains, right? Partly because our humans visual system are also biased and they are not perfect, right? Like our visual system also suffer from some obvious mistakes, right? Like illusion, or like a lot of interesting diagrams you will see on Twitter saying, okay, the roller coaster is moving or the cross is moving, but it feels like your brain feels it's not moving at all, right? So I think every system has its own issue. And what we can do is try to make the deep learning system to be aligned with our human vision system, but I don't think like entire alignment is possible. But in other domains, I think it may be easier to define what is the in domain, what is out of domain, right? Like a lot of people start looking into this malware domain where they know a code is malware or not, or there is an oracle that can tell you it's a malware or not. And but we don't have that luxury in images, right? Because it's very difficult to tell an image is it's really in domain or out of domain, right? So I think it really depends on domains, and in some domains where the adversary or normal data can be clearly defined, we can certainly make more concrete progress there.
I also want to add, like in many applications, you have humans in the loop, right? So if you have some images detected as an adversarial example, or an outlier, if a human looks at those images, it can easily say, okay, this is an adversarial example because basically it looks like a cat, but my model is detecting it like a another object. But the other image, it looks like a different environment. It's a snowy environment, or it has some rare features in the image, and that's probably more likely to be an outlier rather than an adversarial example.
And also I want to add another opinion. So if we just want to distinguish the failure example versus adversarial example from the accuracy, from the number, it's very difficult. So therefore, we need to expand our output space. In addition to accuracy number, you should also include other outputs, for example, salience region. So you need to understand why this example becomes leads to the wrong decision. The mechanism used for the adversarial attack to make the decision wrong could be different from the natural example caused the misclassified phenomena. So therefore, we need to expand the output space to have a better understanding about the mechanism to why this is called this wrong decision, to distinguish the system failure versus the intentional adversarial attack.
Okay, yeah, thank you. And also, I like Soheil's opinion on the human in the loop idea. So I think to make human in the loop like system or models, we need to have we need to make the models interpretable. And I know Soheil, you have been doing some interpretability work, right? And so we've been talking about adversarial machine like robustness, but trustworthy machine learning, maybe interpretable is another important issue, as you mentioned. So I've heard people say that we shouldn't care too much about interpretability because in many cases, we humans don't know why we make certain decisions. Yeah, because those decisions can be very complicated. And similarly, deep neural networks can be very complicated. So trying to interpret them is very hard and sometimes can even be misleading. Yeah. So do you have any comments on that? Should we really interpret? Yeah.
Yeah, I kind of disagree on the point of view that interpretability is not important. I think at the end of the day, because we deploy these models, these AI models in practice, in interactions with humans, in order to build trust between humans and the machines, we need to be able to at least explain some reasoning behind some of the predictions or some of the actions model take. And interpretability can come in different forms and shapes. You can think about input interpretability, for example, highlighting what were the important features using certain predictions. Or you can think about like models that can inherently interpretable. For example, if you go, a little bit back and not use neural networks, for example, decision trees are quite interpretable because you can explain the way that the prediction rules are happening in the model. Say, okay, so I'm looking at these features. If it's above a threshold, it's below a threshold. These are the rules that I'm using. And I think in many applications, for example, if you're applying for a loan and your loan application is being rejected, I think you are entitled to understand why the model has made that particular prediction, and also help you in order to improve your application for the next time. Right? So these are real world consequences to have explainability in the model. And I think, it's not going to give us focusing on only robustness or focusing only on very narrow aspects of trustworthy machine learning is not going to lead to very practical applications of AI systems in human life. So, I think it is extremely important to consider all of these aspects and also interactions among them. As I mentioned, you can even have a reliable interpretability model or method, and you can apply some adversarial robustness to it. You can say, okay, so I'm going to, understand if my explainability signal is actually robust towards like some adversarial or maybe random perturbation. So those are interesting problems that I think, hopefully many of the students listening to this panel will start thinking about that.
Thank you, Soheil. So I have a follow-up question. So at CVPR 2019, there was a workshop called Computer Vision After 5 Years. And in that workshop, Professor Alexei Evros from UC Berkeley talked about there are some research areas that he regretted he did in the past because those research didn't create much impact, but that brought many people into the field and resources into those fields. Yeah. So, and he said one example is a graphical model. He should have used neural network earlier. And he also gave some predictions on areas that he will regret working on in the future. And I think there are four areas, and including adversarial machine learning and explainability. The other two are vision plus language and data sets. But yeah, so the two areas, adversarial machine learning and explainability, he thinks that he might. So for example, say after 10 years, when we look back, he thinks maybe we will find that we shouldn't put too much attention on these questions or areas. Do you have any opinions on that?
I cannot disagree more. I think both of these areas, I completely respect, people's opinions, and, they're entitled to it. But I cannot disagree more. I think both robustness and interpretability and other aspects like fairness, privacy, they're extremely important. Of course, we have a lot of challenges in terms of, evaluations of these measures, how to evaluate interpretability, in a scalable fashion if you don't have humans in the loop, how, you can think about robustness, not particularly tied to a particular threat model. Of course, we have a lot of challenges, but at the end of the day, we need to understand these problems. We may end up having completely different methods and completely different techniques in 10 years to tackle these problems, but I wouldn't, go and say we shouldn't, study these problems. Of course, I would like to hear other panelists' opinions on this topic.
Yeah, I think I totally agree with Soheil. So actually, I was, like I mentioned, I was kind of working in some companies, and interpretability is actually very important for people. Because in practice, it's not like machine learning is not like a closed system. Because you just run a model, get a prediction, and everything is done. You need to look at the prediction and understand what's going on, and then try to find how can you improve your model. So actually, how to understand the model is very important. But I think there's also difficulty in how do we define interpretability. But that's also a research question. If we can get a very good, universal, a very good and very useful definition, then I think this will be a very important problem.
Yeah, I feel the same, right? Other than all those sufficient conditions, I think it's an important research question on its own. I don't think a lot of them will be solved very soon. Other than that, I also want to highlight this necessity, right? A lot of government regulations and law requirements actually require your AI technology to be explainable, right, and to be robust, right? So you have, as a model developer, right, in the industry, you have to practice those guidelines and make sure your model or the service you are deploying will meet those guidelines, right? So it's not like okay, this is not a research problem and hands off, right? It's like it will just become more and more practical.
Yeah, another important application for model interpretability is actually in the medical domain. So in the medical image domain, a lot of doctors actually appreciate interpretable machine learning decision. Rather than just give me a number, tell me yes or no. So I think this is important, maybe not very important to an expert in computer vision, but it could be very important to non-machine learning experts. Yeah.
Yeah, thank you. So we have another question from Haibin Wu. Haibin is asking any future directions for the newcomers in adversarial machine learning, or we should focus on more practical questions about robustness, such as distribution shift, as Professor Cho-Jui Hsieh mentioned. Thanks.
Yeah, I think there are many open questions like what all the panelists are talking about. So I was talking about the distribution shift because I think that's a very practical question we face. But I think there are, like for newcomers, I think there could be, so even if you just focus on like a LP non-robustness, but if you can make some breakthrough in like well-defined problem, I think it's also some good contribution. Because I think why people are using LP non-robustness, because you can imagine in the future there may be some way to define your perturbation set by, for example, I think Soheil mentioned you can define your perturbation set by some like either autoencoder or generative model, and then the things we develop for LP non-robustness can also transfer to those settings. So I think either way will be very meaningful. Yeah.
Okay. Anyone other want to talk about other future directions?
Yeah, so I just go back to the last two slides I had, right? Don't do this marginal thing. I would hope this new generation will be something more impactful and more like far-reaching than us instead of doing this marginal thing, including myself. Yeah.
Yeah. Oh, yeah. Speaking of slides, yeah, I think there's a student asking if we will have released the slides. Yeah, I think so. If you agree, we'll collect the slides and put it on our website. Yeah. Yeah. And okay, so I've a follow-up question on this. So the pace of like adversarial machine learning is very fast. A lot of you can see a lot of papers on arXiv every day. So sometimes for newcomers, it's very hard to keep up with the latest advances or keep up the latest trends. Do you have any suggestions on to our students on how to succeed in this field? Yeah.
I think this is also challenging to myself.
Yes.
Yeah, every morning, if you look at the Google Scholar, and they recommended a lot of articles, so it's very difficult to follow. I guess it's I understand it could be very challenging to new studies, but at least my experience is you should understand what you want to do. So, for example, personally, I'm really interested to advance the theory and practice of defense mechanism to diverse set of attacks. So therefore, I just focus on that sub areas and just look at the articles in that sub area. And I believe the Cho could just focus on the verification part. So then this will reduce a large amount of papers, right? So find the good sub areas and focus on that and trying to make an impact to the field. I think that's important. That's my suggestion.
Anyone want to also comment? So if not, due to our time constraint, I think finally, maybe each of the panelists, can you give some suggestions or like maybe general suggestions to people who want to work in the field of trustworthy machine learning? Any general suggestions or comments? Yeah. Maybe you can go, Ms. Sijia, you want to go first? Any other suggestions you want to make?
One suggestion is I think working on trustworthy machine learning, this is not just application. You also need a very solid mathematical background. So therefore, this is not just a publication and doing impairments and doing sanity check for every criterion for the robustness, not like that. So you should build a solid alternation and mathematical background. And this is a general field, and build up the basic knowledge and make it strong. And then this will make you not just survive in adversarial machine learning, but also in other domains. So that's my suggestion, focusing on the fundamental things and try to make yourself with a stronger research ability.
Okay. So Soheil, you want to talk?
Sure. So I'll just follow up on Sijia's point. I think understanding some fundamental aspects of robustness is important in terms of, provable robustness, certifiable robustness verifications. But I would say we are kind of, going beyond the point of considering very simple problem setups in robustness. If you're starting to think about some of these problems, you should think a little bit about more general and practical formulations in terms of generalizability of robustness, in terms of considering more practical scenarios in terms of adaptivity of the adversary, in terms of online learning, so on and so forth.
All right, thank you, Soheil. Pingyu, you want to add some final suggestions?
Yeah. I think both Sijia and Soheil made a very good points. I want to add that if for a newcomer, right, maybe we should look at some areas that are less explored. Right? I think nowadays for adversarial machine learning, we focus a lot on like images and text, right? But there are certainly other domains and modalities that deep learning is excelling and become better and better, right? Like a time series or even tabular data, right? I think those are domains of very practical importance, and most of the a lot of industries are using that kind of data modality. But and also there are more advanced deep learning models being developed for those modalities. But those domains, probably because those data are not really publicly available or not, it's just not drawing enough attention. But certainly their adversarial robustness or how to improve their models generalization on the distribution shift and so on are very important problems.
All right, thank you, Pingyu. Corey, you want to say something?
Yeah, I think I have similar opinion to all the others. One thing is, I think for newcomers, you probably want to know exactly what you want to do. So from the definition to the problem you want to solve, because given there are too many papers and there are many fancy titles, it's very easy to become lost after browsing all the titles. You think everything has already been done, but actually some of them may not be like carefully defined, or maybe it's like if you start from the definition, maybe you can have your own idea. So especially because there's exponentially growth of the papers, I usually ask my students, don't be like so you need to be self-confident, that like a little bit to define your own problem and believe what you're doing is important. Yeah.
Yeah, thank you, Jory. I totally agree with you. So a lot of times when you have some ideas and you just Google it, you will find there's an archive paper published 2 weeks ago and on a similar topic, similar title, but don't be like discouraged. Maybe after reading the paper, you will see that there's still difference and there's still space that you can differentiate your research. Yeah, so. There's definitely a lot of things you can do. Yeah. All right. So yeah, thank you very much. Due to the time constraint, we will finish this panel discussion session. So thank you all the panelists today. Thank you for joining us and have the wonderful discussion. And we will collect the slides from you, and we'll put the slides on our website and also our Facebook group. Yeah. So, and also we have the poster session later today. So please join all the students if you want to interact with other fellow students. Please join the poster session later. Yeah. All right. Thank you very much for joining us today. Yeah.
Thank you very much.
Yeah. Have a nice day. Bye bye.
Bye.
Bye.